Hello everyone. This project is entitled Stochastic Differential Equations for Performance Analysis of Wireless Communication Systems. Its idea is to use SDEs to find the distribution of the fade duration, which is the duration during which the signal remains below a given threshold. So if we have X solving this SDE, and if Z of t is the fade duration in the period 0t, then we can express Z of t as the solution at final time t of the following ODE. And this is the expression of the Z of t. So let us first investigate the Rayleigh fading case. It's the case where the amplitude has Rayleigh distribution. So if you have the signal psi expressed in terms of in phase and quadrature phase I and Q, and if I and Q are two independent OU processes satisfying this SDE, then we can prove that asymptotically I and Q are Gaussian variables with mean 0 and variance sigma square over 2. And then the amplitude has Rayleigh distribution with parameter sigma over square root of 2. We can also show that in the stationary regime, the autocorrelation of the process psi is given by this expression, so it's decaying exponentially. Now, if we want an SDE for the amplitude itself, or for the square of the amplitude, I mean I square plus Q square, we can see that the SDE describing the evolution of this process is non-Markovian. Alternatively, we can use a lower dimensional process obtained through Markovian projection, and to do so, we will use Markovian projection lemma. So if we have psi bar and z bar is a Markovian projection of psi and z, then we can find the drift and diffusion of the SDE for psi bar and z bar using the Markovian projection lemma. And we know also that psi bar, z bar, and psi z for the same initial state have the same conditional distribution. And using Fokker-Planck, we can also prove that psi bar is an asymptotic exponential distribution, which is exactly the same distribution as psi. Recall that we need to have the distribution of Z of t. We will use two methods to do this, Monte Carlo and Kolmogorov backward equation. So let's start by Monte Carlo. We will merge this SDE for X and this ODE for Z to have two-dimensional SDE. We'll use Euler-Maruyama approximation of X and Z. The CDF of Z can be written as the probability of Z of t less than W, the parameter of the CDF, which is the expectation of the indicator function. And then we can use just simple average using different samples of Z bar at the final time Tn using this discretization. For the Kolmogorov backward equation, we will introduce a new random variable Z tilde equal to W minus Z. But this is just to reduce the number of parameters. And then X and Z tilde solves this new SDE. And similarly, the CDF is this probability, which can also express as with Z tilde, and we will call it U of Tx Z tilde, which is this expectation. We know from the Kolmogorov backward equation that U solves the following PDE. So just some details about how to solve the PDE. We will fix some boundary conditions, and we will discretize in X, Z, and T. And then the vector of unknowns have this equation. So we know from the backward equation the solution of U at the final time t. So using this backward equation, we can solve it several times until getting the solution at the initial time state. And then the solution, the CDF, is by taking X equal X0 and Z tilde equal W. Now I will show some numerical results. We use these two approaches to estimate the PDF of the fade duration in the Rayleigh fading case. We took two different values of the threshold gamma, and for each case, we varied the value of B. B controls the autocorrelation of the signal, so the larger B is, the less correlated the Xi process is. And we can see here that for smaller threshold, the PDF is shifted to 0. And for when we increase the value of B, the PDF becomes wider.